Numerical integration is desired for working with finite elements. The integrals involved in the stiffness matrix and the equivalent nodal load vector are too complicated to do by conventional integration. The standard integral that we use is the Riemann integral, and here we're going to replace it with sampled points on a function multiplied by weights. We'll give the background of the Gauss integration and show its use extensively in one dimension. We'll talk about Radau and Lobato integration, show how you can extend to non-symmetric domains. We'll talk a little about two dimensions and finite element applications, which is the real use of the method here. And we'll have some problems to illustrate these different cases. We'll start out by looking at integration of a real variable on a one-dimensional domain. So it's going to be a function of x. Generally speaking, you would have this function f shown as a dashed red line extending through your region of interest. I'm showing it dashed because I don't really know that function explicitly. I can sample it, though, at specific points on this axis. The goal is to find the shaded area under the curve. And of course, as we mentioned in the lecture on interpolation, the difficult part of finding that area is to characterize the function, because the three straight sides of this figure are not difficult to find. It's only bounding it at the top. So what we're going to do is replace the conventional Riemann integral on the left here with this finite sum on the right. And that sum has only n terms rather than infinity. It has weights that will emphasize our different samples, and then the value of the function that is being sampled at these coordinates x sub I. Sometimes these sample points are called abscissa, and I'll use the word sample point and abscissa interchangeably. One author, Hamming, says that numerical integration follows in four different paths. The first type would be integrating a function by sampling at fixed points. And there are two emphases here. One is that you are only evaluating the function, and that these fixed points are predetermined perhaps by making the points evenly spaced. A second method gets something like a primitive derivative through differencing. A third approach would actually calculate derivatives as well as the functions. Now, evaluating the derivative is going to even be more expensive, but there are methods that need that. And lastly, our methods, and Gauss integration is characteristic of this, that require samples of the function at specially chosen sample points. Now, these are not equally spaced. In fact, these are optimally chosen to reduce error. Let's look at a concrete example of numerical integration. It's a simple method called the trapezoidal rule. Here, we're looking at samples of the function at evenly spaced points on the axis. And then one imagines that the area under the curve is subdivided into small trapezoidal regions, connected with straight line segments from the intercepts at the top. Then it's relatively easy to sum the total area under the curve using the trapezoidal formula, which says that you use basically the average height times the base of each little trapezoid. An interesting thing is that the left sample point contributes only to the first calculation, but the interior sample points calculate both to the area on their left and their right, and as such are doubly counted. As a result, when you sum up these various trapezoids, you find that the end points have weights that are, in this case, the delta x over 2, but the interior ones have the weights delta x times the samples, and then finally another exterior point. This formula is robust in that it's hard to fool it very much, and I know that rather than using an intricate formula, there are times when you would like to use such a simple rule. And I did that myself once in my master's thesis years ago when I was integrating strain energy in a delta wing to get natural frequencies. And I found that a very intricate rule called Moltop's quadrature that really was complicated. It used fitted sines and cosines and got weight functions, that is, weight constants that were large numbers, both positive and negative. So I don't want to make fun of this simple trapezoidal rule. It is the most robust of all the methods, the least likely to go wrong. A second integration rule is Simpson's rule, and this fits small sections of parabolas through the curve. Here you have to have an odd number of evenly spaced points, and you can subdivide your area into regions that have 3 sample points, and then you can pass through these intercepts at the top, you can pass a parabola. Likewise, with this next area, you can pass another parabola. And without working out the details, the weights come out in a different pattern. The end sample values are not weighted highly at all compared with the middle sample values, and the ratio is 1 to 4. Now, because the end value occurs not only in its own area, but this point will also affect the next one, you then, when you add these up, get the weights going in the ratio 1, 4, 2, 4, 2, 4, 2, 4, 1, because those end sample points are used twice. Now this formula is a little more complicated, a little less robust, but still is useful in many cases. Now let's look at Gauss integration. This is a very efficient method. The sample points are chosen for accuracy, and when that's done, you get essentially twice as much value from each sample point. So it's a little like magic, but it's a logical approach where you say, where can I put these sample points to give me the most accuracy? And the answers are sometimes surprising. They're often irrational numbers, so they're not necessarily evenly spaced or nicely spread across the domain. Now, for practical purposes, rather than looking at a general definite integral running from A to B on the x-axis shown here, let's instead look at a symmetric domain extending from -1 to 1. Then the function will be defined as this dashed line over that region. We'll use a variable xi as our integration variable. Later we'll learn how to do the calculation on the unsymmetric domain, which is the more physical problem. But the reason we want to do this is that it's easier to calculate the weight constants when you do it on a symmetric domain, because you have a symmetry in the problem. Let's develop the Gauss integration by considering the simplest domain that we can, namely a one-dimensional space. So we're basically asking for the area under a curve. Here we're going to convert our problem from thinking about a general function, f of xi, on the symmetric domain, into a problem where we have a series of terms that are polynomials. Now this is a legitimate Taylor expansion, so there is some basis for doing this. It makes us think then, rather than some fuzzy question about accuracy of a general function, into a more specific set of questions. How can I best evaluate the integration of a constant, of a linear term xi, of a quadratic term xi? And you'll notice that the expansion in the Taylor series involves these coefficients, but they play a rather placid role outside the integral. And so if we can resolve how to integrate these polynomial terms successively, then we'll know how to calculate a general function. The usual approach here, and it's logical, would be to require that you integrate successfully the longer wavelength terms first, much as you would in a Fourier analysis. So we would demand, first of all, that you can integrate a constant, then secondly, that you can integrate the quantity c, then c squared, and on up in the polynomial series. When I first wrote down the replacement of an integral of the Riemann type with a sum of sample points and weights, you might have noticed that each sample point generates two unknown constants in that process. One is the weight to be ascribed to the sample, and the other is the location of the sample point. And so if you have n sample points in a Gauss integration, you're going to have 2n constants to be evaluated. Now, I repeat that here by saying n sample points are going to generate 2n unknowns. You'll get n weights and you'll get n abscissa. Now, the way that we're going to evaluate those constants is by creating what are called defining equations, and these are the conditions that the integration process be exact for the various terms in the expansion. So for various polynomial terms. And if we have n sample points, we're going to have 2n unknowns, and we're going to need 2n defining equations to get the job done. Now, I think this bookkeeping I've just done is a little bit unmotivated, so you'll see it from the examples that follow. The simplest example we can start with, and now we're really going to generate a replacement approach here. It's a replacement sum that is going to be used instead of this conventional integral. So we'll have to find a weight, w, and a point at which to evaluate the function c1. There are two unknowns here, and then we're going to require two defining equations to evaluate them. We now set up two defining equations based on accuracy need, and that will give us two equations to find these two parameters that we seek. The first defining equation physically is just that we ask that we can integrate the area under this curve here. And it's on the symmetric domain from -1 to 1. Mathematically, it's expressed by this law that we must be able to integrate unity from -1 to 1 and get an exact answer. What is the exact answer? The exact answer is 2, because it's a 2-unit area here. The way I'll do this is basically work on both sides of the equation and come down from above and put in what we know about this sampled function. Now, it turns out no matter where you sample on this axis, you're going to get a unit value as your intercept up here. And so therefore, I'm okay to put a unit value there, and that immediately gives you that W1, the sample point, is the number 2. The second defining equation is a statement that we must evaluate C exactly. And over here I show the picture. This time it might seem to be a trick in a sense that the total area is 0, which I show on the left. But that's a useful concept. Now, no matter where you sample, at some sample point C1, you will go up and you'll intercept the curve, and then move to the sample point here, which is F at C1, and that will in every case turn out to be the number C1 itself, because it's a 45-degree line. And so we have our second equation. Since we already know W1, we can see that C1 should be 0. And so putting that back into our original representation of this integral, we find a weight of 2 and a sample point of 0. Well, we have our first Gauss integrating formula in our hand, and now we have to find something to do with it. So let's look at some examples. Here's our integrating formula. It would be called a one-point integrating formula, and we could use it perhaps to integrate some function, such as this straight line function here, 3 plus xc. I'll show it as a solid line here because we know what it is, but nevertheless we're going to evaluate it by sampling. Now, it really seems like a little much to say that if you multiply by 2 a sample value at the origin that you're going to get an exact answer. But we know that from our defining equations we can exactly integrate a constant and then a linear function. So we're going to get an exact answer if we take a sample at this location of c equals 0, find the intercept, and on that function the intercept will be the number 3. So I'll put in here 2 times 3 is 6, and that will turn out to be exact. We can check that by doing the conventional Riemann integral and finding that indeed that is the area. Or you can use your common sense and see that that number sampled at the value of c equals 0, or an abscissa of 0, is actually is the same as this enclosed rectangular area, which is 2 units wide and 3 units high, and so we know that rectangular area is going to have 6 units. And then you can see that on the plus minus side the actual function will contribute equal positive and minus terms over and above that particular rectangle. So either logically or doing the integral in the conventional way, you can prove that this is exact. The previous example was an easy one because the function that we were integrating was a linear function, and the integrating formula could be used exactly. Let's now consider that one-point formula applied to a higher degree polynomial, such as this red curve shown here. When you use the integrating formula we've developed so far with only one sample point, you are asked to sample at the origin here. You find this intercept, and effectively what was done was to block out this area shown in the rectangle here. And you can see that that area will underestimate the true area of the more complicated function. So sadly in this case our one-point formula underestimates the answer. So this can happen and often is acceptable because you would rather do a cheaper integration and have some error involved in it than to carry enough sample points to do an exact solution. Now we can make some conclusions in one dimension. When you have n sample points, you know that requires 2n defining equations. And if you satisfy 2n defining equations, you're satisfying sequentially the polynomial terms 1, xc, xc squared, and so on, up to 2n minus 1 in polynomial degree, where the minus 1 comes about from the need to integrate the constant term. So you can actually tell how many sample points you need when you're integrating in one dimension. On the other hand, if you have transcendental functions or higher degree polynomials, then your answer will be only approximate, but that's quite often acceptable. You might also have experimental data, which typically, for instance, in some problems could be Bessel functions or area functions, some other actually infinite series in polynomial terms, and again, that would just be an approximate answer. Let's now look at a two-point Gauss integration. This will require 2 sample points and 4 defining equations. So we replace this Riemann integral with these 2 terms. The defining equations include the previous 2 in philosophy, namely that you have to integrate this rectangular area under the unit value. And as we found before, that was 2 units. Now we have 2 quantities to evaluate here. Since the sample will give you a unit value no matter where you sample on the axis, you get units there, and you get this first defining equation. The second defining equation, again, has to do with areas under the linear curve, which is 0 because of cancellation. And when you sample at point C1, the functional value becomes C1. When you sample at C2, the functional value becomes C2, which I show here and here. So our second defining equation is this one. And notice that the variables are coupled together. The third defining equation has to do with integrating a parabolic function. Here we show the parabola on the symmetric domain. We can do the Riemann integral directly and find that it's an area of 2/3. When we evaluate the function c squared at the points c1 and c2, we get these 2 values of c1 squared and c2 squared and get this new defining equation. Again, rather seriously coupled. Lastly, the fourth defining equation is an integral over a cubic polynomial. Again, you get by cancellation a 0 integral exactly, but the approximate value is shown on the right. So we really have 4 nonlinear equations in 4 unknowns. This is a relatively tough problem to solve as it stands, and I'm going to take a shortcut, which is a fair one and which is correct. Namely, that if we're to choose 2 sample points on this domain, is it likely that they would be bunched up on one side? No, they'd probably have to have one on one side and one on the other. Is it likely that they might even be symmetrically disposed? And the answer is yes, because you have no idea where that a true function that you're integrating, a general function, would fly through this space. It might go this way, or it might be the mirror image the other way. Therefore, it is correct to assume symmetry that the 2 sample points are equally spaced about the origin. Now, that relation can be used to eliminate one of the 4 defining equations. Because of that simple symmetry equation, we now can ignore the 4th of the defining equations. It's pretty complicated because it has cubics. We go into equation 1 and solve for the one weight in terms of the other weight. And that plus the symmetry condition we'll put into our equation 2. So this was a location where W2 would have occurred. And then this is the location where C2 would have occurred. So we're using all the information at our hands now. And when we do that, we end up with an equation 2C1 times the sum W1 minus 1. Now, there are 2 potential solutions here. One would be that we take C1 equal to 0. But that wouldn't be useful because then C2 would also be 0, and we would have 2 solutions or 2 sample points bunched at the origin. So no way are we going to sample the function twice in the same spot. We know that that's not the optimum way. So clearly the other solution is the proper one, which gives a unit value for the weight. And then using the equation above, we find the other weight has to have the same value. We didn't prescribe this, but this symmetry was obtained as a result of our process. Now the third equation then can be solved for the sample point because it was C1 squared times W1 and then W2, which is also unity, times minus C1 squared. And adding that together, there are two of those, so it equals 2C1 squared. Then the 2's cancel, and you get C1 squared equals 1/3. Or, as shown here, C1 is the square root of 1/3, which is an irrational number. Now, naturally, you wouldn't try to locate that point with such terrible precision. I've just carried, enough numbers to impress the viewer, I guess. C2 is a negative of that, just to show that they really are spaced symmetrically about the origin. Our integrating formula for a two-point integration now becomes the integral of this general function on a symmetric domain is unity, which was the weight, times a function evaluated at plus 0.577, and then a weight of unity times a function evaluated at minus 0.577. And since we were able to satisfy four defining equations, that means this integrating formula is exact for a cubic, 2n minus 1. Okay, well, we need to nail this down with a numerical example, so I'm going to pick kind of an exotic example here and see if we can exactly integrate it. Suppose I do take a cubic, which our new formula should exactly integrate. What I want to do is evaluate this expression numerically. This is a pretty tough function because it's a cubic. It has 3 zero crossings, which is the maximum that a cubic could have in that region between minus 1 and 1. I show it here with a heavy blue curve, and we're trying to find the area under it, which is a positive area in the red crosshatched regions and a negative area in the green crosshatched regions. So, knowing how to Gauss integrate, you could take this curve into your neighborhood bar and say, I can integrate better than anybody in the bar, and then take bets and so on. Well, I think the people would be astounded if they learned that you could take a sample point at plus 0.577 and all those decimals and come up here and take this one spot, and then you evaluate at minus 0.77, etc., and find this spot. And if you told them, all I have to do is add this number on the left and this number on the right, and I'll get the exact area under that curve. Well, naturally, they wouldn't believe you, because who'd believe an engineer in a bar anyway that's doing too much bragging?